Okay, so like in the last time we did the force and moment balance. So like now we're basically considering the same thing that we did for strain 2. That is, now we're considering for stress. So like we're considering stress in different direction. So like if I consider any arbitrary direction and cap and tau cap, so I can basically write the stress tensor since like stress is a tensor. So like we can apply basic laws of linear algebra. So like sigma prime in the new coordinates would be like q transpose sigma q, right? So like if I consider a general rotation, like if this are my x and y axis, then basically if I consider a rotation to x prime and y prime axis at an angle theta. So like obviously I can apply this transformation matrix. This transformation matrix Q would be the like as we said, we cos theta minus sin theta and cos theta, right? Cos of theta, sin theta, minus sin theta, and cos theta again. So basically, after applying it twice on the sigma currently, so like this is the xy wala sigma, and like this sigma prime would be the new sigma in terms of x prime and y prime. So like that would consider this x prime and y prime as its new coordinate. So like I can write sigma prime is equal to sigma x prime, sigma y prime x prime, sigma x prime y prime, and sigma y prime y prime. So basically this new sigma will have, and let me just erase this uh, for some reason here. Hmm. So now that we have this sigma, so we can apply these two tensors on this and sigma, and like we'll get the sigma x prime component. So like sigma x prime component in terms of sigma x component is this. So like the derivation is like really not important. You can basically do it on your own too by writing just by doing the tensor matrix multiplication for twice, and you can like basically simplify it to get in this form. So like you have sigma x prime is equal to sigma x cos square theta, tau xy sin 2 theta plus sigma y sin square theta. And similarly, sigma prime y would be sigma x sin square theta minus tau xy sin 2 theta and sigma y cos square theta. So like they are kind of similar. And we have this tau xy is equal to half sigma y minus sigma x sin 2 theta and tau xy cos 2 theta. So basically, you can just find the new component and their strength in terms of the old component sigma x prime in terms of sigma x. Now for uniform strain, like suppose we have sigma x is equal to sigma y. So in that case, anything sigma x is equal to sigma y and tau xy is equal to 0. So in that case, we have sigma x prime is equal to sigma y prime is equal to sigma x and is equal to sigma y, and which can be seen from this equation too. Like sigma tau xy would be 0, and the sigma y prime and sigma x prime cos square theta plus sin square theta is equal to 1. So like basically all four components in any direction, if when we see, they would be the same. So like other cases are like this sigma x is equal to minus sigma y. So in this case, tau prime x prime y prime would be equal to minus sigma y. But like these are like some special cases which you can just directly substitute the values. Like I mean, if sigma x is equal to minus sigma y, just put it in here and you'll get the answer accordingly. Like you'll get this tau x y prime, this would be 0, and then you'll get basically the answer in terms of this. And the second thing is the same as the principal direction. So like as we did in strain, we can find the principal direction at which the like the stress values are maximum. So like the principal directions at which the stress values are maximum occurs at this theta. So like this tan to theta is equal to 2 tau xy upon sigma x minus sigma y. So basically at we can find the angle theta at which it will be maximum, and the maximum value would be this value. So like the derivation for this is basically very simple as we did in the strain 2. Like these maximum and minimum values are the eigenvectors for this, and like the direction are eigenvectors, and these are the eigenvalues for maximum and minimum are eigenvalues. And since they are eigenvalues, they are basically called the principal directions for the stress and strain. So like if you have sigma x and sigma y, you can basically find this theta at which sigma x would be maximum and sigma y would be maximum. for these cases. So next up we have a Mohr circle, which is also basically similar, kind of corresponding to it. So like basically for Mohr circle is like an old was used in olden times when there were no computers as such to calculate the stress and strain values. So basically what we did in Mohr circle was we plotted our initial state of stress. So like if our sigma x and tau xy are here, so basically we drew the sigma and tau. So like this is a graph. So basically we plotted sigma x and tau xy on this, and like we basically kind of plotted it in the opposite direction too, with sigma x and minus tau, sigma y and tau minus tau xy. So basically we know that sigma x prime is equals to half of sigma x and this, and we can basically like now consider half of sigma x plus sigma y as an another constant a, and half of sigma x minus sigma y, since like we see it's occurring here. So like considering them as a new constant, we get sigma x prime is equals to a plus b cos theta plus tau xy sin 2 theta. And like now if we consider, we if we look closely, it's like a kind of an equation for a circle. Like if we basically consider it this time, and like kind of basically add both of them, squaring and adding. So like basically this cos theta and sin theta terms are eliminated, and we finally end up with this equation of circle. So like basically you can see that this is a kind of circle centered at a comma 0. So basically the center of the circle is at half of sigma x plus sigma y, and its radius is b square plus tau xy whole square. So like b is this and plus tau xy whole square. So basically now if you have this, then if you have this initial sigma values, then you can basically plot a circle near it at a center. At the center would be like this a comma 0. So like half of sigma x plus sigma y, you can plot the center. You can basically find this direction and you can plot the entire circle. So like for any theta, now you can find the basically the values at which the stress and strain would be, like the sigma x prime you can find, and tau xy prime you can find using any point on this circle at any angle. So like this is our initial direction. So like at any angle theta, we can basically find that sigma and tau values using this Mohr circle method. So yeah, that is I guess the content which was for this video, and I guess I'll see you in the next video.